So more good news is to add vectors using this component form of vectors, the A, A1, A2. Good news. If A is A1, A2, and B vector is B1, B2, it's very easy to combine vectors, add, subtract. Yeah. A vector plus B vector, you know, you do the initial point of one to the, or the terminal point of one to the initial point of the other. But if you got the components, it's just a matter of adding them. And we can go through the adding the components. So it's very, very simple to add vectors that are in this component form. Yeah, if you look at the diagram, it all makes sense. Subtraction, same thing. And scalar multiplication is easy. We'll talk about multiplying them, and next time. But yeah, subtracting, very much the same. If I'm doing A minus B, you just subtract the components. A1 minus B1, and then A2 minus B2. Very simple. It's easily provable geometrically there. If you want to look at that, but suffice to say, yeah, that's the way it works. And then multiplying it by a scalar, well, that's easy too, because if you want to multiply it by a number C, vector A, then you just multiply each component by that scalar's amount, C. So it'd be CA1 and then CA2. Those three, anyway, are similar. And then 3-dimension is analogous, okay? Just add the third component if you've got 3 dimensions. So those are all pretty nice. All right, so let's just do a couple of quick calculations here. All right, so we've got A is 3, 2, -1, and B is 4, -5, and 0. Let's just do this first, all right? What would that be? What does that mean? Magnitude of A, right? The length of A. So do the length of A, magnitude of A. It's that square root of all the components squared. So you do 3 squared plus 2 squared plus -1 squared. Of course, that's going to make them all positive. 9 plus 4 plus 1. So that'd be the square root of 14. So that vector would be square root of 14 long. They usually want it. I don't think they want you to round it off usually. So anyway, square root of 14 long. What would A plus B? Those two vectors added together be? Well, like I said, we didn't write it down, but to add 3-dimensional vectors, you're just going to add the corresponding components together. So we're going to add the first component, so 3 plus 4, 2 plus -5, and then comma, -1, comma 0. Sorry, -1 plus 0, that's going to be a third component. Yeah, so if you add 2 vectors, you get another vector out. I guess we didn't point that out, but yeah, if you the magnitude is just a number, but if you add 2 vectors, you get another vector out. 7, -3, -1. And then, yeah, the other thing that I'll have you do is this anyway. Yeah, this is subtracting 2 vectors, but I also multiplied them each by a scalar, and so I would take 6A, so that would be what, 18, 12, and negative 6, subtract from that 4 of b, so it'd be 16, negative 20, and 0. That way you could look at it, right? 6 times those, and then 4 times those, and then I'm going to subtract those. Well, subtract them, I'm just subtracting the components. 18 minus 16 is 2. 12 minus negative 20, that would be actually positive, wouldn't it? 32. And then negative 6 minus 0, 6. Does that sound right? Okay. So yeah, we can do that sort of thing fairly easy. All right, now, another way to represent, or let's start this way. We can also use what are called standard basis vectors to represent vectors. Standard basis vectors. There's three, well, in 3 dimensions, there's 3 standard basis vectors. You've got the I vector, which is just the vector 1, 0, 0. Standard base. So basically what that does is it breaks out, if you will, one piece of it. This would just represent kind of an X vector, a vector in the X direction. You know what I'm saying? So 1, 0. So you have 1 in the X, 0 in the Y, 0 in the Z. So yeah, you just got a 1 unit long vector along the positive x-axis. So that's one of the standard basis vectors. It's 1 unit long, but it's only in the x direction. Well, then you got the J, which is the counterpart, where you're only going in the y direction. So it'd be 0, 1, 0 vector. And so that would be the vector that goes in the positive y-axis direction in 1 unit long. Standard basis vector, and then you've got the of course in the z direction. Zero, 0, 1. So that would be the vector. 0 in the x, 0 in the y, and then 1 in the z. So you're only, I guess I'm going to draw those two. So yeah, that one's only 1 unit long in the y direction. This one's 1 unit long in the z direction. All right, well, so what do we do with those? Well, those give us another way to represent vectors. So if I've got A is A1, A2, A3. And of course, here I'm doing these in 3 dimensions, but you can back up and do it in 2 dimensions too. But that would be equivalent to A equal A1 times the I vector plus A2 times the J vector plus A3 times the K vector. So this IJK, adding those 3 vectors and then using the A1, the A2, and the A3 as the scalar multiple, if you will, times those, that's going to be the same vector. Because if you think about it, all right, so this would be A1 times 1, 0, 0. This would be A2 times J is 0, 1, 0. And this would be A3 times 0, 0, 1. Well, if you perform the multiplication there, you got A1, 0, 0, right? This would be 0, A2, right? 0, just multiplying. You just multiply it in, and so that stays 0, that's A2. And this would be 0, 0, A3. Well, if we add those three together, A1 plus 0 plus 0 is A1. 0 plus A2 plus 0 is A2. And 0 plus 0 plus A3 is A3. Ta-da, okay? So this is another way of writing a vector. 7, 5, -2 vector is the same as 7i plus I vector plus 5j vector minus 2k vector. So that this is another way of representing a vector. Okay?